In this lecture, we will continue with the inferential statistics, recalling that in the last few we were discussing hypothesis formulation and the aspects that are involved in that. But today we will be looking at sampling techniques and the different types of sampling techniques that we can use and what issues arise with those sampling techniques. So the objectives that you'll get an understanding of those sampling techniques as they pertain to the hypotheses that you formulate regarding the statistical tests that you run, how to select the right sampling technique, and we'll have some hands-on experience with real-world data using Python. So the flow will have the sampling techniques, some of the issues that arise, the pros and cons within these sampling techniques, and what are some of the aspects we use in screening the accuracy of those sampling techniques, one of which is the confidence intervals, and then have a practical. So we did start off with descriptive statistics, which summarizes the samples, okay? But now we need to go a little back forward and understand why we do the sampling and how we can use it to make inferences for the wider population, okay? And this is where the inferential statistics comes into play. So in essence, we're testing the statements or hypotheses about the populations by using the sample data. And we use sampling because it does have an aspect of being more inexpensive, less strenuous, and also more convenient because we have situations wherein we cannot access the entire population or sometimes do not know the actual number of the entire population. So here we will be, okay? We started off with the hypothesis formulation and testing. And you recall we had the example of the undergraduate varsity level of education, and we are making a statement. If the average age of graduation is 22 in a district like Kampala, we can use that information to make inferences about other districts within the country of Uganda, okay? So zooming out from a sample of Kampala and broadening to a population that's wider. So we'll start off with one of the techniques called simple random sampling, wherein every sample or member of the population has an equal probability of being selected. Since the sampling is random, it does have an advantage of being simple to implement, but it does have the disadvantage of creating sampling errors. And these could result from the fact that the randomly selected sample may not be an accurate reflection or representative of that population. For instance, if you are running a census using this technique and you are specifically targeting a particular group, for instance, people living with disabilities, you may have some misreporting, or within your random sampling, you have respondents who are not living with disabilities. So that can skew and create bias within your data and your analysis. For the stratified random sampling, there's a different approach. The population is first divided into random groups or strata, and these strata can be criteria-based, which you'd have to make as a decision beforehand. It can be based on gender, and that's why you hear a lot of people talking about data being gender aggregated. It can be based on age group and other types of criteria, depending on what question you are seeking to address. Then a random sample is taken out of that strata or grouping. Now, the advantages here is that they ensure precision because you've tailor-made it to that particular study. But the disadvantage is that they require some prior knowledge. So once one is using this technique, they must have some prior knowledge about that community that they are sampling or that experiment that they are sampling from. For instance, if you have a research project that is targeted at understanding the performance of university students between the ages of 18 to 22, and you are sampling just this group, okay, you can choose a criterion that is gender-based. So you would make sure to include males and females, having prior knowledge that there are actual males and females in that community that range between these age groups. In cluster sampling, you have what is a probability type of sampling. It's suited for larger populations, especially those that are spatially divided, spatially referring to different geographical groups. So the approach here is that you divide them into the non-smaller groups that are referred to as clusters. We will see in the practical, these clusters are referred to as K, and they're geographically based. For instance, if we go into a country scenario, you can cluster them into districts or parishes. They do have the advantage of being more robust towards larger populations or larger groups and larger studies. However, they can also have some creation of bias, especially if you've chosen the wrong groupings, okay? We can have an example where you are trying to look at how many people practice coffee farming within the country of Uganda, and you decide to use the cluster sampling approach, and you're specifically targeting the major producers, okay, like Mubende, Zombo, all the way to Iganga. Now, what if there are other districts that do practice and they haven't been represented in your sample? This could create a bit of bias about your data. We also have the systematic sampling. The approach here is that you select samples from a population at predetermined regular intervals. So these intervals can be time-spaced or number-spaced or order-spaced, okay? For instance, if you have in a shopping mall and you're trying to review your customers' perceptions about the products, you could choose the 11th customer if you decide. So every 11th customer that walks in, you could seek out reviews from them. In a laboratory experiment or a medical study, you could choose maybe the 5th lab rat out of every 1,000, or choose the 5th lab rat for every time you have that entire grouping or population of 1,000. The bias here that can arise with systematic sampling is as a result of having no order. If you haven't ordered your samples, then the patterns will appear in a dissimilar way and can create some form of bias. There's also convenience sampling, which is one you've all had an experience with because it's based on sampling a population based on their availability when they are ready or willing to provide that review or that response. When you're in a mall and they're seeking out your reviews on a new product, it's only because you walked in or you're available or willing to even participate in that survey. So this one tends to be simple and inexpensive, but it's quite highly prone to bias. So how do we choose the right sampling method? We do this to minimize bias as much as we possibly can, and we do this based on certain aspects. For instance, we have to know the entire population size, but in some instances we might not know, and that distribution. So again, the descriptive statistics come into play. For large populations, cluster systematic sampling is more practical. Another aspect that we use to determine the method we choose is the type and availability of resources. Simple random sampling can be expensive, so you would be considering something like a convenience sampling, which would be cheaper. The level of precision that we desire, we do design all statistics analyses a high level of precision. So stratified tends to improve the level of precision. Again, the population diversity. Okay, if you have different types of groupings within your population, you want to be able to have a proper representation of those groupings. So stratified sampling would be the best approach to go. How do we then estimate what is the right sample size? There are aspects of point estimation because sample size is very, very key in statistics. It can make or break it for the end result and the accuracy of your statistics, okay? So we do this and determine the sample size using certain key aspects. We can measure the confidence interval, or otherwise referred to as error of margin, which measures the degree of uncertainty or certainty in a sampling method. For instance, if you have a survey sampling 1,000 respondents within a country, and you have a confidence interval that is ranging from 6 to 60% of the sampled respondents that are showing you that they have a positive review about that product. That implies that to infer it to the entire population of that country, okay, up to 54%, which is as a result of 60 minus 6, or 66%, which is 60 plus 6 of that entire population, feels positively about that product. We also have the confidence level. This is a percentage of probability of certainty about the confidence interval. And it is expressed as a percentage and represents how often the percentage of the population would pick that particular answer in the regards of the example referred to of positive response to a product. For example, if you have a 99% confidence level, it means that every time you go back and redo that study, there will be a 99% probability that those respondents will still feel positively about that product to the percentage that you had it at the particular confidence interval, okay? Even if it's done by another scientist in stretched out to a wider population, there's a 99% expectation or likelihood that the respondents will give you exactly that same result. We also can use standard deviation. And remember, standard deviation looks at how the data set's distribution is from the mean. And it's used to calculate the sample size. So it's useful in estimating how much the responses you receive will vary from each other and vary from the mean or average. And the higher the distribution of variability, the greater the standard deviation you expect, or the magnitude of that deviation. So once you set out for your survey, you should have some kind of prior knowledge as to how varying the opinions of that population is, okay? So how do we calculate this? Of course, now it sounded very abstract, but there is an actual formula to this, okay? We use the population size if we know it. We use the confidence interval, confidence level, standard deviation. If we don't know the standard deviation, the safer point is to go for 0.5. And then we can also convert the confidence levels to create z-scores, which are used in calculating that sample size. And there is a formula for calculating sample size when we use Andrews-Fisher's formula and those z-score tables that do the conversions. So the formula looks like this. When you have the z-score, you have the standard deviation represented by the p, and you have the error of margin, okay? So you can always refer to the confidence and z-score conversion table, which you can find online. However, if you don't know the population size, or you do know the population size, for instance, you are looking at a company that has 500 people, how many do you want to sample? You can use this alternative of a formula which includes the population size at hand, okay, that is represented by n. So we will now go through the practical session of how every one of these sampling techniques is used and applied to different data sets, okay? So in the first instance, we will begin with the simple random sampling technique. Remember, we have to have our libraries, NumPy and Pandas. Now we're going to use these to create a random population. And in this data frame, we're creating a random population of up to 100 samples, okay? And these 100 samples have varying variables. We have 4 variables. We have an ID, age, gender, and income, okay? So the ages are randomly generated, and we are choosing ages between 18 and 70, okay? Remember, our total population size is 100 individuals. We are also randomly choosing the gender to either be selected as male or female. And the incomes, we're giving that a random range of from 50,000 to 10,000, okay? So we get to see at our data frame and what that looks like. So we just get the first few rows, and that is what it looks like. Now, we're interested in the age and its distribution. So we can plot that out using a library, matplotlib or Seaborn. And we are specifically just looking at age. So that would be highlighted in the color sky blue. So we can see that distribution over here. It's not normally distributed. It's almost similar to having a bell curve, but we do have some issues somewhere. That is what it looks like. So we want to take that entire population and use random sampling, and we can determine how many random samples or individuals we want to look at. Let's say we choose 20 random individuals. We create a function for which we are calling that function simple random sampling. We then call up our data frame, which is named population, and we have the parameter n. N can be determined based on how many individuals we are sampling from that entire population. In our case, we are choosing 20 individuals, okay? And we want this function to return both the population and the sample. So we go ahead and use that function to do a sampling of 20, which is done randomly. And this is the resultant data frame, okay? So notice the IDs that it has chosen are very, very random. They are not in some sort of order. So now we want to create a visual, a histogram that is superimposing these age distributions of the population versus the sample. So create a histogram, and we're looking at the population itself, and the random sample that contains 20 individuals. So population is represented in the blue, and our random sample is represented in the salmon or pink, depending on the type of device you're holding or your visuals. So we can see that with sampling 20 individuals, okay, there are some representations that look very similar to our population, but we also have those regions where there's some missing bits of information that are not representative of the entire population. For instance, between the ages of 57 to 59, which is from here to there, and 65 to 78, or close to 70 rather, we can see that there is some missing information that the sample doesn't cover. So it does have some bias to it. So we realize we could try and check a different option. What if we increase that sample size? What if we increase it to 40? Okay. When we increase it to 40, this is the image we get. Or we're having the missing information here between 50 and 60. That has been represented, but we still have some missing information over here. So one is informed then that when they do a random sampling of this entire population, they need to do a bit more of an increase in the number that they sample. Let's look at real life data, our bike sales data set that we have been working with the entire time. We had the customer ages. Let's look at their distribution, and let's try to use that for a random sampling. Okay, so we see the distribution of our customer ages is not normally distributed. It's skewed to the right. Let's perhaps sample 20% of that entire data set. Remember, the entire population has up to 113,000 plus samples. So at 20%, we are looking at 22,000 customers, okay? So using the same formula or the same codes that we have been using in the past, when we superimpose the histograms, we have the population and the random sample that's represented in green. We can see that 20% is managing to represent the entire population. It mimics the same pattern that the population is displaying in terms of the visuals. What happens if we try to go lower, maybe to 1,000 samples? Okay, that's so much, much, much lower. Okay. When we do that, we have our sample size down here in green is not representing the population. It is creating a lot of bias. Okay, so now we know that when we are dealing with this type of data set, we need to go a bit higher because it's a big population. What happens with stratified sampling? Remember, stratified sampling divides the population into strata or groups, okay? And then from those groups, we select a random sample from each of the groupings, okay? And this method is suited to populations that are highly diverse in key characteristics. And we can see with our bike sales data set, it's quite diverse in the amount of variables that it has, the amount of information that it portrays. So let's look at that. We create again a function for the stratified sampling. And in it, we have our data frame, which we call data. We have n, which would be a number of strata or groupings that we are creating. And we use the stratification function. So what happens when we apply that function. When applying that function, we have to have approaches, okay? We want to know what our total sample should be. We want to sample only 1,000 customers, but we're taking different percentages from each group, okay? From each age group, or from each customer age. So we are deciding that we're taking from the individuals that are 20 years old, a percentage of 20%, those that are 35, a percentage of 30%, and so on and so forth, varying percentages for each of these ages, okay? That are done randomly as we have decided. These are our strata, okay? So we generate our stratified data or group data, and this is what it becomes, our subsetted data of the 1,000 total samples. Now, we want to see the representation of this sample data versus the entire population. In this scenario, we are using the bar plots, okay, to generate that output, okay? And this is what it looks like. We have our population in blue, we have a sample in orange, okay? And we can see the portions for each age. So you have 20 all the way to 60, and the portions that we specifically selected, okay? In some cases, when we look like around 50 and 60, the representation is not quite similar to the population, but for the most part, the sample does mimic the population. What happens with cluster sampling? In cluster sampling, you have the entire population. You create clusters within it, okay, from 1 to all the way to 12. These clusters, when you write the function in Python, would be referred to as Ks. Now we take these clusters and we randomly pick any number of clusters, okay, that you would have determined. In this case, we're choosing 5, 6, 11, and 12. And we're looking still at our bikes data set, and we are clustering based on the country where the samples or the customers come from. So we try to see how many countries there are. We can see that there are 6 countries